so you realize this is the only two things you need to know about calculus, and it's summarized over here, right? So just to reiterate that, right? So if you differentiate x with respect to, if you differentiate something with respect to x that has a power, you have two steps. First, you drag the power down. That's step number one. And then step number two, you decrease the power by 1. Okay. And for integration, you reverse the process. So instead of dealing with the power, instead of pulling this down first, you first go and increase it by 1, and then you deal with the coefficient. You deal with the number in front, but instead of multiply, you divide. And you, instead of, you see here, you multiply the old one. Now you divide a new one because it's always the opposite, right? So you can just check that if you differentiate this, you will get back to this, right? So the two steps is reverse. Here you first pull the power and put it in front, and then you decrease it. Here you increase the power first, all right? You even reverse the order of it, and then instead of times, you divide and also divide a new one. Okay, and remember to add c because when you integrate, you have multiple options. Okay, so what does this have to do with kinematics, right? So it all stems from, so now let's connect this to kinematics, right? So it all stems from, remember the definition in kinematics when we had the definition of average velocity and average acceleration, right? What is the definition of that? Well, this was defined as the change in x, the change in position, how much position you've changed in how much time, and the average acceleration is how much velocity you have changed in how much time, right? So that's displacement over time, right? Over the time taken, that's how much you change. However, that's only average, right? Because things can change if you look at the graph on x and t, right? It can change along the way. So what about instantaneous velocity is dx dt? It's basically the slope of it. This was the slope of the xt graph, but now you look at the slope at a specific point, right? So same thing, acceleration, instantaneous acceleration, we call it dv dt, right? So the conclusion of this part, right, what do we conclude is the velocity is the slope of xt graph, right? And acceleration is the slope of the vt graph. Okay, so you see, general, right? This is the how much on the xt graph when you plot it. That's how much x changes. If we put x on the vertical axis and t on the horizontal axis, how much x changes with respect to time. That's the slope. But that's just the average slope because in the middle it can change. So if you shrink that limit to look at a point, and that is the, so you can add yourself in the notes. I'm not going to rewrite this. Instantaneous velocity is the instantaneous slope on the xt graph, right? Average velocity is the average slope. So you look at the average between 2 points. You just take the difference in height and difference in difference in x and difference in t. That's the average slope. So instantaneous, just add instantaneous slope over here. All right. So remember, finding derivatives is finding the slope. So that's why the velocity is the derivative of x. All right. So imagine I know x of t. So this is a function. This is called the position function. V of t would be, if I can find it, it will be called the velocity function. A of t is the acceleration function. So these are my key players in kinematics, right? So if I know all these, actually, this is what I want to know the most. That is the sort of the holy grail of not just kinematics, but all of physics. We want to find the position at every given time. So this is a function. So if you input the time, if I can find the position function, that means any time you give me, I'll tell you exactly where it is. If I have these as well, I can tell you the exact velocity of it and the exact acceleration, right? So see how powerful these functions are. And you realize that v is just dx, the x function, right? With respect to, not x, with respect to time, okay? And this is differentiating v, the v function with respect to time, okay? So if you know this, I can just do derivatives and then find these two, all right? Or if I know this, I can integrate and find these two, all right? So which way round should we go? If we remember, in our problems of interest, do we know X or do we know V or do we know A? What are the problems we've been interested in so far? We've been interested in a very special class. Even though it's very special, it's not limited because a lot of motion satisfy that. And remember, it's the constant what? Constant acceleration motions, right? We're interested in motion of constant acceleration. That means A of t is a constant, right? It's going to just take one value. I'm just going to call it A, right? Without any function. So it almost says acceleration changes of time, but it does not, right? So I'm going to assert that A of t is just A, right? So you see the function is independent on t. Whatever t is, it's still going to be A. A of t is always A, all right? So given this fact, can I find the rest? And the answer is yes. All I need is this simple fact. And I can find the velocity function and the position function. So the velocity function, well, how do I get the velocity function from the acceleration function? If I differentiate the v, I get a. That means if I integrate the a, I get v. So to get v, I need to integrate a with respect to t. All right? So how do I do that? Well, that is just a constant, right? So the first step, let's write it like this just to make it less intimidating. And then now we think about integral. So integral is the reverse of the differentiation. So what differentiates to give a constant? Well, I propose you just add a t to the power of 1, right? Differentiate this, you get this. Remember, if you differentiate 2x, you get 2. Differentiate 5x, you get 5. So differentiate at, you get t with respect to t, right? These are with respect to x. That's why there's a slight discrepancy there, but I hope you can see the connection. And what am I missing? Whenever you do integral, you should always add c. You should always add any flexible constant over there. All right. So that is we'll figure out what is c in a moment, but essentially that is the velocity function. All right. Looks a bit weird, but let's press on. How about the position function? Because that's the holy grail, right? We want to know where things are at every given time in the situation. Imagine knowing the projectile, right? Every single position. Tell me 1 second later, I know exactly where it is. 10 seconds later, I know exactly where it is. That's the one we're looking for. So, well, we need to, if I differentiate x, I get v. So that means if I integrate v, I can get x, right? So we can push that one step further. So what is v? Well, we have the expression here. So it's at plus some constant, right? Now, when you add things, because remember in differentiation, you can differentiate it term by term. When you integrate, it's just the same. It's the reverse, right? So you can do it term by term. So first of all, you have a constant here. So a, all right, that's fine. What's integrating t? Because you can ignore any constants in front. You can just deal with a variable first. Well, I'll say it's 1/2 t squared, right? Remember. And what's integrating a constant? C. Well, we've done that already. Just add another t, right? Like this. What am I missing? Whenever you do integral, you need to add a constant. So let's call it d. I've used c already. All right. So that's the position function. And that's the velocity function. It's not complete because I still don't know what c and d is, right? So let's figure that out. But make sure you understand the procedure there. Okay, what is c? Well, I have a nice trick. Let's look at time equals to 0. What happens at time equals 0? Well, so that's velocity of time equals to 0. I plug this in, right? What's the velocity at time equals 0? Well, that's going to be 0. And it's going to be a times 0 plus c, right? So that means it's c, right? So c is the velocity at time equals 0. We have a special name for that. What do we call the velocity at time equals 0? Initial velocity, right? So this is identical to, I'll use V0. That's usually what the books use, right? But in SUVAT, we call that U. That's the same thing, right? That's the same thing as u, but we'll call it v naught just because most books call it v naught if they don't use the SUVAT convention. All right, good. So what I found is c is actually v naught, right? So I have a more complete understanding now, plus v naught. In fact, let me write it the other way around. Write it as v naught plus at, like this. So just swap it around. That's how the books usually write it, right? All right, and so that's the initial velocity, right? You can plug in the time and you'll know whatever time it is. If you plug in the final time, that will be the final velocity. Does that look familiar? Right. Now you might recognize, hey, I remember that. That's u equals to v equals to u plus at, right? So that's exactly the same thing. But here we basically just talked about the final time, and that's the final velocity. And initial velocity like that. So that's the, if you plug in the final time, then you have the final velocity over here. Okay, let's do the same trick over here. I need to find out what, well, I know what c is. I just need to find out d. Let's use the same trick. Let's plug in t equals to 0, right? So what happens if I investigate x of 0, right? So we plug this in, right? So we have 1/2 a, but then this is going to be 0. Right, so that's going to go away. Plus c is v naught, but we're going to plug in 0, so again that's going to go away. And d. Can you notice that this x of 0 is d? Or I should flip that around, and I can flip that around and say d is x of 0. So that's just the position at time equals 0. That's called initial position. We don't have a SUVAT variable for that, but let's call it x naught, right? It's a new thing in the formal approach. So it's a new variable over here. So d is x naught, right? It's the initial position. So now let's rewrite this. X, the position function. In fact, let's go from least power to highest power, right? So I'll start from d and then t to the power of 1 and t to the power of 2. So I'll start from x naught plus v naught of t plus 1/2 at squared. And this is the position function. Okay? Do you recognize that with any SUVAT equations? Yeah, of course, right? Because it takes a little bit more finessing, right? You need to put this on the other side. And that means if I plug in x of t final, then this would just be the final time, right? The position at the final time, this is the position at the initial time, is equals to v naught t plus 1/2 at squared, or final, right? If I'm plugging in final time, that the final position minus the initial position. What's that? That's delta x, which is s, displacement, right? So we have s, this is what we call u, right? T is just the final time in our equation. And we have this, s equals to ut plus 1/2 at squared, the one that we use a lot, right? So as you can see, these are the two formal kinematics equations. And right in my full, right? So you have this, you can, so I'll just summarize. You have this one, you have this one, like this. Sometimes people want to be even more explicit and write this as depending on your starting time. Your starting time does not necessarily have to be at t equals to 0, right? You can start at a different time. So you can write it like this. And you can write this as t minus t naught plus 1/2 a t minus t naught squared. And you can rearrange this to get the other two as well. What was the other one? I think it was xt minus x naught, right? Is v of t plus v naught over 2 times t, I think. Average velocity, yeah, that makes sense. And vt squared is v naught squared plus 2a x of t minus x naught, right? So these are the 4 kinematics equations in the formal approach. As you can see, it's really ugly to memorize, and you can probably tell I don't have these memorized. I'm just sort of working backwards, but essentially these two I've shown where they come from. How do you get these two? It's just the same thing. You eliminate A, right? Here you have no A, so you take the first two, eliminate A, you'll get this. Here you have no T, so you take the first two, eliminate T, and you get this, right? So T minus T naught to be depending on your starting time as well. So they have their use. You'll see them in your discussion sessions. When are they particularly useful? However, of course, you can identify most of the time, if you're being clever, you can use SUVAT variables. So this would be S equals to V plus U divided by 2 over T. So that's the average velocity equation. And you have the 2AS every time you see X minus X naught, basically, right? So anytime you see X minus X naught, that's S. And any V naught is U. All right, so that concludes our study on kinematics. And the whole idea, I think, is basically just do a lot of problems, and you'll see the pattern. We just to summarize, right? We have learned how to use the net force to find acceleration. And if the net force is constant, so in the special case of constant force or constant acceleration, right, by Newton's second law, then we can derive these equations, which are extremely useful to predict the future given the initial conditions like that. All right, so once you have mastered all this, we'll go and look at how we can apply this to the real world, what we can learn, and make some good predictions about different scenarios in physics. All right, so have a great weekend, and I'll see you in the next lecture.